Let us now study the production of induced EMF by changing the area of the coil. Okay, so now we have a uniform magnetic field. Okay, so this is the magnetic field here. It's given by B. It's pointing into the board. Okay, so you can see that magnetic field is represented by a vector. Okay, and then it's pointing inward into the board means we can see the tail feathers here. So that's why we write as X here. Okay, now let us see an equation for it. Okay, so you can see what is this one. Production of induced EMF by changing the area of the coil. So we have a coil here. Okay, this is a piece of wire. Okay, bent in this shape here, like a rectangle shape. This end is open. Now we take another wire here. Okay, so this is a piece of wire here. Let us name this wire as A, B. Okay, this part is B, and then now what happens? We are going to move this with a velocity V. Okay, this part, and after some time it will come to a new place here. Okay, so let this new place be C and D. Okay, so it comes to new position here. So let the length of this wire, okay, from here to here only, let the length of the wire be L. Okay, and then let's see what's the distance it travels. This distance we must know. Okay, so we know it travels with velocity. Okay, so first we must know what is the formula of velocity or speed. Speed is equal to distance by time. Distance by time. So we write here V is equal to distances. We don't know distance. Write as distance here. Time, we know that small time only. Okay, it travels small distance only, you know. So small dt. So we can write here V into dt is equal to the distance it travels. So this distance it travels is what it is, V into dt. Okay, this you must be very clear. Okay. Next, what happens is we will go to the equation here. Okay. Let us see what is the change in the magnetic flux here in this region. Okay. So change in the magnetic flux. Okay. So magnetic flux symbol is what it is, phi. A change means red D and then phi B. A change in the magnetic flux. Okay, B means magnetic flux. E comes in, we write electric flux. Okay, so this will be the magnetic field into change in the area. Okay. Change in area. Okay, area dA. The small change in the area now. That one. So we can see that B into what is a small change in the area? This one. Okay, the small change here in this part, that is A, B, C, D is a small change in the area. So the area A, B, C, D. Okay, that's part. Next, what happens is we must know that since this area, okay, since the area, okay, this one A, B, C, D is equal to, we must see this thing. Area means what it is. Okay, so distance into length will come. Okay, area means you can say, you know, how it comes is you can say it's like a rectangle. No? ABCD is like a rectangle. That means the length into breadth. Okay, so you can see it now. It is like this way now. This was length and the breadth was V dt. Okay, so area means length into breadth. Okay, so that's how we get here VL into V into dt. Okay, length into breadth formula. Okay, now let's go to this side here. Okay, so let us see this magnetic flux here. Okay, so now we have this thing. Okay, so let's substitute here. Okay, substitute the value for area. Okay, value for area ABCD. Okay, in this, that is equation 1. Okay, in equation 1, so substitute here and see. So here d phi b is equal to b into, and here we have L and V into dt. Okay, BLV dt. Now what happens is we take this dt downwards here. So we get here d phi b by dt is equal to BLV. Okay. Now from Faraday's first law, okay, second law, sorry. Okay, from Faraday's second law, Faraday's second law, we have that epsilon or EMF is equal to d phi b by dt. Okay, so compare that and see E is equal to, okay, BLV. Okay, so this is, you can write here, this one you can write as equation 2. How it comes is from equation 2. Okay, you see d phi b means BLV. Okay, so now we have this thing, EMF is equal to BLV. Okay, so let me erase the left side now. And then before going to left side, okay, this EMF is there now. Okay, it's caused by the motion of the conductor, so it's called as motional EMF. So B means what? The magnetic field. L is the length. V is the velocity with which this AB part moves that side. Okay. Now let's see. This direction of current is given by the Fleming's right hand rule. Okay. So let me write it also. So direction of current is given by Fleming's right hand rule. Given by Fleming's right hand rule. Okay, let's apply that and see. Okay, so Fleming's right hand rule states that stretch the three fingers of right hand. Okay, mutually perpendicular. Forefinger shows the magnetic field, middle finger shows the induced current, and thumb shows the force of motion. Okay, so the forefinger points the direction of magnetic field like this way. Okay, then the thumb shows the direction of motion like this way. Okay, and then the current is shown by like this way. Okay, so current goes from A to B like this. In this side, it will go from D to A. Okay, that's how it comes clockwise. So current direction is here, I. Okay, this is the direction of the current here. So easy. Next, what happens is we will see if R, this loop has a resistance now. Okay, so if R is the resistance of the loop, okay, resistance of the loop. Let's see what happens now. Okay, so current I is equal to V by R we learned. Okay, from Ohm's law. We write as E by R now. Okay, the EMF by R. So EMF we have VLV. So we get here current I is equal to VLV by R. Just substitute the value of E. Okay, how it comes is substitute value of E. Okay, or the epsilon. Okay. When you substitute that, we get this value for current also. So now we have two things. We have got the EMF and we have also got the current induced if you move this conductor from one portion to next portion. Okay, so this happens, what happens, we are changing the area of the coil here. Okay, you can see that it's changing the area. Okay, so in this way also you can produce a current here or an EMF.